All right, so the information we need from the structure of the unit cells of ionic compounds is that when you have a closest packed structure, the anions are the larger ions. So usually, most likely, the anions are the larger ions, and so they're packed together in the closest packed structure. And that closest packed structure will have one octahedral hole and two tetrahedral holes for every one anion in the structure. So, all right, I think that the simple cubic structure is probably the easiest one to start with. So let's take a look at a simple cubic structure. Remember, that is the kind of cube where there is one sphere at each corner of the cube. So these four yellow spheres are like the four corners of this cube. These are in back, so I'm trying to draw a three-dimensional structure here. And then they've raised up these four, so it's not really a cube. This should be lowered down, but if it was lower, it would hide this blue, the blue cation that is in the cubic hole. And so the way that the unit cell is drawn, since you kind of are drawing these extra pieces of the yellow anions, it almost looks like there's one cation or one cubic hole for every 8 of these anions. But if you look at the structure, we don't just have one unit cell, we have a repeating structure. And so if you look at the structure and maybe even draw in another, row over here, we have the cations being the smaller ones in red, the anions being the larger one in blue. We have cesium chloride here. So we have 16 of the chloride and 16 of the cesium. So we have a 1-to-1 ratio. So these are the octahedral holes, really, are what these red things are representing. And so for every one blue anion, we have one red octahedral hole. So there's one octahedral hole for every one anion if you go out and repeat the structure enough. If you look at the unit cell, it can be a little bit misleading. So the shape of a tetrahedral hole, if you look at these yellow spheres as being the anions in a closest packed structure, this yellow sphere is going to sit right on the divot that's formed from these 3 yellow spheres. And so that's going to squish the top of this red hole until it looks kind of like a tetrahedron. So that red hole will kind of look like a 4-sided dice. So one of the sides is not showing, but you can kind of imagine like a 4-sided dice, a tetrahedron that's pointed downward. That's the shape that would be made by these spheres coming together. This particular drawing doesn't make it look like there's 2 tetrahedral holes for every one yellow sphere, I think because they haven't colored in all of the possible tetrahedral holes that there are. But that's just a visual of what the shape of the hole would look like. Here is a visual of what the octahedral hole would look like. So we don't have one sphere that's coming down and squishing this blue hole. What we have is a twisted, relative to this base of 3, we have another 3 that are coming in. So if you imagine the blue part of this hole that's sticking down into the wedge between these 3 is kind of making a little triangle thing pointing down into that hole. And then when these 3 come down on top of it, there will be another triangle thing pointing up into this hole. So this is kind of, instead of a flat squish triangle, we have a triangle facing up and a triangle facing down. So this is kind of a larger hole. And again, drawn as a single unit to try to show the shape of one hole and focusing on one hole, we have 6 of these anions, 6 of these spheres coming together to show one hole. But this structure is extended in a repeating pattern. So if we look at just this part of this layer of sodium chloride, we have 1, 2, 3, 4, 5, 6 of the anions, and then we also have 1, 2, 3, 4, 5, 6 of the holes for the cation to go in. So it's a 1-to-1 ratio between the octahedral holes and the anions. So I don't know, it's kind of hard to draw and visualize these holes, but the take-home message again is the ratio of anions to holes. And then I just wanted to give credit of where I got these drawings from. So here's the website that I got them from. Let's go ahead and use these to try to solve a problem. So we're going to use the information that this closest packed structure has 2 tetrahedral holes for every 1 anion, and the anion here is oxygen. Then if we use charge to reason out the formula between sodium and oxygen would be 2 sodium for every 1 oxygen, because we have sodium with a +1 charge and oxygen with a -2 charge, so this has to be the formula for sodium oxide. So from the formula we get that for every 1 anion, there are 2 sodium cations. Then if A equals B and A equals C, then B must equal C. So if 1 anion equals 2 tetrahedral holes and 1 anion also equals 2 sodium, we can reason logically that 2 tetrahedral holes equals 2 sodium, and then we can simplify that ratio. Instead of a 2-to-2 ratio, then there's a 1-to-1 ratio between every tetrahedral hole and a sodium. So there's 1 sodium for every tetrahedral hole. So all of them are filled. So logically we can come to the conclusion that all of the tetrahedral holes are filled by sodium. All right, so we mentioned that with a simple cubic structure, we don't have tetrahedral holes and octahedral holes, we have simple cubic holes. We have cubic holes. And there's 1 cubic hole for every 1 anion, like we saw in the drawing. And so we're told that half of these cubic holes are filled by the cations, the uranium cations. So 1/2 of the holes are filled. For every 2 holes that you have, 1 out of those 2 is going to be filled. That's what 1/2 is telling you. So if half of the holes are filled, then out of every 2 holes, 1 of them is filled. 1 out of every 2 holes is filled. So we're being told that for every 2 cubic holes, we have 1 uranium cation. So we don't have an exact match like we did in the previous, where we could just say A equals B and B equals C, so A equals C. What we have to do first is double this first line here. So if there's 1 anion for every 1 cubic hole, then it follows that there's 2 anions for every 2 cubic holes. So now we have an A equals B and C equals A, so we can equate B and C. And so we have that for every 2 anions, there's 1 uranium cation. And so that would make the formula, since we list the cation first, UO2. So we have 1 uranium for every 2 of the oxygen anion. So it's a 1-to-2 ratio. So the formula would be UO2. Okay, so this is the maybe trickiest one that people were looking at. So we have oxygen in a closest packed structure. Oxygen is our anion, and it's a closest packed structure, so for every 1 oxygen anion, we have 2 tetrahedral holes, and also we know that we have 1 octahedral hole for every 1 anion. And we're told that magnesium cations occupy 1/8 of the tetrahedral holes. So for every 8 holes that we have, 1 out of those 8 is occupied. So 1 out of the 8 holes has a magnesium in it. There's a 1-to-8 ratio between magnesium and the 8 tetrahedral holes. And then the last piece of information we're given is that there's 1 aluminum for every 2 octahedral holes. 1/2, or 1 out of every 2 holes, is occupied by aluminum. So then the next thing I would do is try to make these match. So if we have 2 tetrahedral holes and we have 8 tetrahedral holes here, I would go ahead and multiply this by 4. And then I know that I have 4 anions, which is oxygen, for every 8 tetrahedral holes. And then I'll try to match the octahedral hole and see how that comes out. We're going to multiply this by 2. So we have 2 anions for every 2 octahedral holes. And those anions, remember, are oxygen. All right, so we have these 2 matching. We have the magnesium and the oxygen sort of set to match the ratio where there's 8 tetrahedral holes. So the one thing that's not matching is the octahedral holes. So I'm going to go ahead and make this match. So right now I only have 2 anions. I'm going to go ahead and double that. Then I'll have that 4 anions is 4 octahedral holes. And the reason I did that is so that the 4 anions would match the 4 anions here. So now what I have matching is that 8 tetrahedral holes equals 4 anions, and 4 anions equals 4 octahedral holes. So I have this equivalent statement down here, which makes sense. If you think about it, for every 1 anion, you have 1 octahedral hole and 2 tetrahedral holes. So with 4 anions, you would have 4 octahedral holes and 8 tetrahedral holes. So this seems to be true. This seems to make sense. I don't think I've messed anything up here. So looking at our other statements over here, what does 4 anions mean? The anion is oxygen, so we have 4 oxygen. And then the 8 tetrahedral holes, that equals 1 magnesium. And then the 4 octahedral holes, I want to relate that to aluminum, so I probably should have doubled this first. Let's go ahead and double this. 2 aluminum equals 4 octahedral holes. So 4 octahedral hole would mean 2 aluminum. So our formula must have a ratio of, for every 1 magnesium, we have 4 oxygen and 2 aluminum. So our empirical formula would be 1 magnesium, 2 aluminum, and 4 oxygen. So that took a little bit of multiplying of the ratios to get something where everything could agree, and we could get the right ratio of 3 things to each other. But hopefully all the things that I've written here make sense. So this one might seem pretty easy compared to that other tricky one. We have the anion in this case being hydrogen, which is kind of weird. We usually see hydrogen as a cation. But for every hydrogen anion, we have 1 octahedral hole. The formula tells us that there's 1 potassium for every 1 hydrogen, and hydrogen is the anion. So these are written in a different order here. I guess I could fix that. So for every hydrogen anion, there's 1 potassium. And so now we can see that since A equals B and C equals A, B must equal C. So we have 1 potassium equaling 1 octahedral hole, meaning there's a 1-to-1 ratio between potassium cations and the octahedral hole, so all of the octahedral holes are filled. So that's the answer to the question of what portion of the octahedral holes are filled. Out of every 1 hole, 1 is filled, so they're all filled.